Okay, so hello everyone. And this week we're very happy to have Nancy Aggarwal here from Northwestern University talking to us about gravitational wave detection at above LIGO frequencies. So yeah, go for it.
Cool. Yeah, thank you, Robert. And thanks a lot for inviting me to be here. It's a great pleasure to be talking to y'all. But like my first caveat will be this is my first time talking about this experiment. I mostly focus on talking about squeezing. So we'll see how this goes. Yeah, so my main where I will tell you today about this gravitational waves experiment to look for gravitational waves at 10 kilohertz and above. This we're doing it with a team of people, which is shown here. So there's main 3 PIs involved: Andy Geraci, Vicky Calogera, and Shane Larson. And here we're like collaborating with Sierra, which is the astrophysics division at Northwestern, as well as CFP, which is the fundamental physics division of Northwestern. And while I'm at it, I would also like to acknowledge all the funding sources for this effort, which is the Keck Foundation, the ONR division, as well as NSF. Okay, with that out of the way, just sort of an outline of what we will hear about today. So I'll build up some context and introduction for why this experiment and what it is about, and I'll show you the design as well as some details of what the main noises are going to be in this experiment. And then I'll show you like some recent work that we've done on improving the sensitivity of this experiment. And I'll compare that and put it in perspective with sources. If there's time, I'll present my latest calculations on what kind of statements can we make if this detector were to run on the abundance of primordial black holes. And finally, I'll wrap it up with some future directions. Okay, so for context, well, today we'll be talking about gravitational waves. You all are very familiar about what they are, but they're basically just ripples in space-time created by objects that have an accelerating quadrupole moment. And on here, on the top left, what you're seeing is a measurement that was observed by the LIGO collaboration, which was the gravitational waves coming from 2 colliding black holes. This was observed roughly 5 years ago now. So I guess this is a good time to take stock of the whole field of gravitational waves and ask ourselves, what have we learned in the last 5 years? So I thought I might summarize that in one slide. Of course, this is a full talk in itself, so I'll only give you some of the examples that appeal to me, I guess. So the first example of what we have learned using gravitational waves that we didn't know before is the mass distribution of black holes. So in this plot, the y-axis is the mass of black holes, and the blue circles represent black holes that have been discovered using gravitational waves. And the purple circles are the black holes that we knew of from electromagnetic observation. And it's very clear, just visually speaking, that gravitational waves have uncovered a completely new population of black holes that we didn't know existed. And in fact, like we have found gravitational waves from black holes that lie in the so-called mass gap, or that come from gravitational waves from black holes that are too heavy. So we really found new populations of black holes that have implications on our models of understanding the formation channels of black holes nonetheless. Secondly, we also have some detection of gravitational waves from merging neutron stars. Those are shown over here in orange, compared with the yellow ones that are the electromagnetic populations. And so the merger of the neutron star, the first merger itself, in fact, brought us a lot of information on a lot of different topics. For example, we learned that kilonovae exist. We learned some physics of where heavy metals come from. Maybe they come from neutron star mergers. And we performed measurements of the Hubble constant. We performed measurements of the speed of gravitational wave as compared to the speed of electromagnetic waves. And in fact, just that one measurement of comparing the speed of gravitational waves to electromagnetic waves, that measurement itself actually was enough to rule out 300 different theories of like modified gravity and dark matter and dark energy. So just this one measurement ruled out a lot of theories. And this is sort of just to give you an idea of what kind of science has happened in the last 5 years using gravitational waves. And if you had asked us before we turned on these detectors, we wouldn't have been able to predict many of these sciences that we have done now. So basically, like whatever I'm about to present in the next 35 minutes, take it with a grain of salt, in that like once the detector turns on, all of this could be out of the window and we could be looking at completely different physics. So that's a caveat. We don't really know until we turn it on. So, well, talking about turning new detectors on, so we're familiar with gravitational waves in the LIGO band so far. The LISA mission will be coming up soon. Gravitational waves are already being looked at by pulsar timing arrays, and as well as from the CMB observations. But here today we will be talking about looking for gravitational waves at frequencies higher than all of these current detectors. And these use levitated sensors, and we're building this experiment at Northwestern. Just sort of looking at a broader picture, though, recently we all met up in Italy, well, before this pandemic, which still seems recently. We all met up in Italy and talked about high frequency gravitational wave detectors and sources. And that motivated us to write up this review over here, which has a lot of physics of high frequency gravitational waves. And then following that, we have now also started a new initiative for bringing all of the community that of experimentalists as well as theorists of high frequency gravitational waves together, so that we can collaborate in really pushing the wall of the frequency higher and brainstorm ideas and everything. So just to sort of recap what we saw in the review, we provide you some comparison of various high frequency detectors that have been proposed, or someone has thought about something, or someone has built something. We go through all of those and compare which frequencies, which one was proposed to work at, what sensitivity could it have reached, or did it reach if it was already built. And then over here, you see that this levitated sensor detector is obviously featured as a proposed or under construction detector. And then we also compare various sources that we expect to be at these higher frequencies. So this plot shows all the coherent sources, for example, mergers of neutron stars and black holes, and what kind of strains we can expect from them at these high frequencies. And again, it compares with the backdrop of detectors that could be operating at each of these frequencies to show us which detector could put limits in which frequency band. And then these are the two sources that we will mostly be focusing on today, which are most relevant to this levitated sensor detector in that frequency band. And finally, we also showed in this review the expected strain from stochastic sources in these high frequencies. Of course, the strain is expected to be much lower. So first, when we're done putting limits on these other coherent sources, we can actually use the same detectors as long as we keep increasing or improving their sensitivity. We could start putting limits on some of these stochastic sources, and that's going to bring us information about a lot of cosmological or phenomenological questions about the beginning and the foundations of the universe. I'll just take this moment once again to highlight this new initiative. So if you are someone who works in high frequency gravitational waves, please go to this webpage and fill out the Google form, because we will be organizing workshops soon to, again, have more brainstorming sessions like the one that we had last year. Okay, so with that, let's focus on the detector at hand today, which is the levitated sensor detector. This is a miniature tabletop gravitational wave detector, and I show a guitar for scale over here. So really like a meter-long detector that can be put in the lab. It's based on optical trapping or levitation, which basically means that it's going to have to be a resonant detector, and the resonance can be scanned from 10 to 300 kilohertz. In that frequency, the sources that are most relevant turn out to be the black hole superradiance gravitational wave from axions there, as well as gravitational waves from mergers of primordial black holes. But again, take all of that with a grain of salt, because we don't really know what we might find once we turn it on. Okay, so now let's look at what this detector is, how it works, and what are the noises in it. So before we do that, first principle that we should all understand is optical trapping. So optical trapping, you might have heard of it a couple years ago when Arthur Ashkin was awarded the Nobel Prize in 2018 for his work on optical trapping. So the idea is you put a particle in a laser beam and it experiences a potential like this, which is like negative alpha E squared, where alpha is the polarizability and E is electric field. So of course, it's gonna attract itself to the higher electric field regions. So now if I put a particle in a laser beam, it's gonna have some radial confinement as well as some axial confinement from just the profile of the electric field in the laser beam. The radial confinement mostly comes from the Gaussian profile in the radius, and the axial confinement can come from the Gaussian for a free traveling beam, or if you have a standing wave, it will come from the wavelength of the electric field itself. So you can get much stronger axial confinements in a standing wave pattern. Okay, so now that we know optical trapping, how do we use optical trapping to build a gravitational wave detector? To understand that, let's just look at a Fabry-Perot cavity, and I will walk you through some GR over here. So for that, let's put ourselves in the frame of this input mirror here. So let's say that I'm sitting at the input mirror and a gravitational wave passes by in the plane. And if that happens, it's going to change the length of the cavity, or it's going to move this end mirror with respect to the input mirror. And that change is going to be proportional to the amplitude of the gravitational wave. And what that will do is it'll move the antinode of the field, which is this blue sine wave over here. And let's remember the particle likes high fields, so it's going to want to sit at an antinode. So the antinode moves as the cavity length changes. But the gravitational wave also just directly changes the distance between the particle as well as the input mirror. So there is a direct change in the position of the particle. So the ultimate thing that matters is the relative change between the antinode and the particle's position. And that we can obtain by subtracting these two changes in position. And that also ends up being proportional to the gravitational wave amplitude. But as you can see here, this signal gets maximized if the particle is sitting very close to the input mirror. So once you have that displacement, a relative displacement of the trapping potential with respect to the particle itself, you can think of that as an effective force applied on the particle. And that force is just given by k times the displacement. So this force, again, is proportional to the amplitude of the gravitational waves. And if the gravitational wave is now at a frequency that is on resonance with the particle frequency, that is omega t here, then you can get a resonant response or excitation of the particle's position, which we can then measure by using another laser beam, which is shown here in yellow. So again, a gravitational wave could excite the thing on resonance. And when we think about that, it tells us that we should really be thinking of this detector as an optical counterpart of a Weber bar, where gravitational wave is really applying the force, and we have to think of it in the resonant force detection category, as opposed to LIGO, which is a broadband displacement detection. Okay, so now we understand how this thing works. We can put it in a Michelson setup just so we can get rid of common noises like laser noise and seismic noise and whatnot. So we put it on a Michelson to get rid of those. And then what here you're seeing on the right over here is some SolidWorks design for the first generation that we will be building at Northwestern of the tubes and the chambers, and we sort of designed all of this out of what we will be building. So we now understand how this detector works. Let's ask, what are the different noises that are important in this detector? The first noise when we talk about optical cavities is the cavity thermal noise. This comes from just the thermal noise of the mirrors, the substrates, and the coatings. We can calculate that given the temperature and the beam sizes, as well as the material properties of the mirrors. And that comes out to be this dashed green curve, which happens to be dominated mostly by the coding thermal noise of the mirrors. Okay, that's one noise. The second noise that is important is the shot noise of the detection. So we have to look at this particle, we have to observe its position using a second laser. And that laser is quantized and has a Bosonian noise whenever we measure the power of the laser. So that noise is gonna basically scale as 1 over square root of the number of photons in that laser. And this determines our ability to measure the displacement of the particle precisely. The third noise comes from gas damping. So we have this particle that's trapped in a vacuum chamber in the laser, but the vacuum chamber, of course, even though it's at low pressure, it still has some finite number of molecules of gas. So those gas molecules are going to come into collision with the particle, and that's going to cause the gas damping, which looks like a thermal noise. So with an effective damping coefficient that I'm going to call gamma G here. So this is the force power spectral density of the force that would be applied on the particle from gas damping. And the last noise that would be relevant for this experiment would be the photon recoil noise. So again, this particle is sitting in a laser beam. It's going to scatter the photons from the laser beam. And the laser, again, is quantized. So the discrete nature of the light is going to cause some scattering from this particle. And that scattering ends up contributing to another noise, more of a quantum noise that comes from the photon recoil scattering. This basically arises because you lose photons out to the environment that are not captured back into the cavity. So these are the four main noises, and we can put them together on this plot over here, where I've added all of them up in this dashed curve, and we can see that the dashed curve is mostly dominated by the thermal noise, which is the gas damping noise, and it's closely followed by the recoil noise. So depending if you reduce the temperature, you could be limited by the recoil noise. They're pretty close. But the cavity thermal noise is way down below. We should not have to care about that from now on. And the shot noise is only relevant off resonance. So on resonance, we only really have to care about the orange and the green, which is the thermal noise from gas damping and the recoil noise. So from now on, I'll mostly focus on those two. And this is what Andy and Mina did back in 2013, where they calculated the sensitivity for a bunch of different options of levitating spheres and disks in 10 meter and 100 meter instruments. And they calculated these sensitivities for that, where they really only focus on the on resonance point of this noise curve that I've shown on the left, and they scan the resonance frequency and they show you the locus of the best sensitivity for each trapping frequency. So this is sort of the lay of the land of how the detector works and how the noises work. So now that we understand the limiting noises, we can try to now improve the sensitivity. And that's what we have done in this new paper with May, of course. Here we look at some techniques that might help us improve the sensitivity as well as improve the calculations of strain expected from axions or from superradiance. Okay, so a little bit more detail on the limiting noise sources. So I said the noise is limited by gas damping and photon recoil. So here I add them, the two force spectral densities from the gas damping and from the photon recoil scattering. And then you can ask, okay, that's in the force on the particle, but how does it actually affect the strain that you measure from this gravitational wave detector? So if you had to write the power spectral density of ultimately the strain that you would get out from this detector, given some force noise, this would be the transfer function that you would have to apply. And in this transfer function, pay attention to a few things. L is the length of the detector. Chi is the mechanical response of this particle. So given some force, it responds with some displacement. So that's chi. M is the mass of the particle, and omega t is the trapping frequency. So if I put in, if I evaluate this formula SHH on resonance, then what I get is this. So here you have some dependence on mass, length, the scattering damping coefficient, as well as the temperature. So from this, we can see what steps we would take if we wanted to improve the sensitivity. So this makes it pretty clear. is that we would need to lower the temperature to lower the gas damping. We can obviously increase the length of the detector. That's going to help everywhere. We can lower the recoil coefficient to lower the contribution from recoil. And we can increase the mass, which will, of course, help with both of these coefficients. So temperature and length are sort of more dependent on the facilities, what can we really achieve in the lab. Like if we only have a meter long space in the lab, then we can't really do much with L over here. And we could go buy more equipment to cool our thing. But in the meantime, we could try to address these other two factors, which is the scattering recoil coefficient, as well as the mass of the particle. So that's something that we have worked on in this new paper. So let's understand the scattering or the recoil heating. So a sphere, if you trap a sphere in a laser beam, it's going to scatter light in all directions. And that's shown over here in the top left plot, where we're showing the angular distribution of the scattered field from the sphere. And then in contrast, if you trap a disk in a laser beam, most of the scattering from the disk is going to be in the direction of the laser beam. And that's shown over here in the right circle. Again, this is the angular distribution of the scattered field. And you see this pointed pink in the center and pink on the periphery, which means the forward and the back scattering from the disk of the light. So this tells us that if we just put mirrors to capture that scattered light, we could actually reduce the photon recoil from by using a disk instead of a sphere. But then we could even go further. Okay, I've lowered the amount of recoil, but can I even increase the mass? Can I just stack multiple of these disks together to get even more mass, to get even more improvement on the sensitivity? So this is some of the work. These are the questions that we try to answer in this paper. And the first component in answering that question was to do numerical simulations of scattering from the disks and the stacks. And these simulations help us compute this gamma scattering coefficient and really verify that, yes, indeed, if we use disks and stacks, we can have a much lower photon recoil scattering. And then given some scattering loss, you can ask, okay, how big do I need to make the cavity mirrors to capture all of the photons that I need to capture to keep the scattering loss low enough? And when we try to answer that question, we find that mirrors, the more stringent limit would be placed on just making your cavity not be diffraction limited. So if you have big enough mirrors for your cavity to just have low diffraction, then scattering should not be a problem at all. Okay, so photon recoil wise, it seems that stacks should be a good idea. Disks and stacks should be a good idea from a noise perspective.
Sorry,
let's ask.
Can I just ask a question here? So in the previous slide, you were talking about improving the on-resonance sensitivity. For many types of sources, you don't know a priori what the frequency is going to be at. So you're going to want to scan over different frequencies. So for those kind of things, what you care about ultimately is the scan rate to get to a given sensitivity. So you care about both the on-resonance sensitivity and the bandwidth over which you have that sensitivity. How do things scale? How does that scale with these parameters? And also, how do you know how that scales relative to just say a broadband interferometer? If you have something with similar laser power, what is the comparison between the scan rates for the the time average sensitivity for the scanned version versus the broadband version?
I think the best slide for that is this one. So here, what you're seeing is the effect of shot noise. So thermal noise and recoil noise don't care about the bandwidth, right? So they don't have nothing, they don't play a role. They're just broadband noises that stay constant over the band. The most noise that will affect you if you change the quality factor. So first of all, the quality factor is an independently tunable parameter by the second laser, where we use the second laser to read out the motion of the particle as well as cool the motion of the particle, so we can lower or increase the quality factor. So this you should think of it like the width of this resonance or this inverse resonance of the shot noise is somewhat variable or tunable. In this plot, I've used it, I think, a width of 10 or 100, but it is somewhat tunable to a certain extent. Of course, after a point, you start making the shot noise higher, but then you just throw more power in the laser. So
yeah.
yeah.
So do you, for example, if you compared to just a standard LIGO type laser interferometer with the same overall power, laser power in it, do you have some idea of what the sort of scan averaged sensitivity would be compared to this and what it's affected by?
Off the top of my head, I have not done a comparison of the scan averaged sensitivity, but one thing I can say is that power in this setup is fixed by the trapping frequency that you want. So it's not really fair to compare. Yeah, it's not really fair to compare it to LIGO power. And so, for example, for 100 kilohertz kind of a trapping frequency, we're looking at maybe 100 watts to a kilowatt of laser power inside the cavity. And in LIGO, we're at a megawatt inside the cavity. So the power is very different. And the scan rate is decided by the power in the meter beam. And that also is quite different from LIGO. Like we are at much lower powers from LIGO.
So that's kind of what I wanted to understand, because from sort of normal like laser interferometer type energy bounds, you'd expect that lower powers would lead to lower frequency averaged sensitivity. That's the sort of usual intuition.
Not in this case.
Okay, so it'd be interesting to understand how, because that's just based on very basic sort of quantum like sensitivity things. So it'd be interesting to understand
if you were limited by the shot noise, right? LIGO is limited by the laser shot noise of light inside the cavity.
Yes.
That's this. So in the blue curve, you see this curve coming up over here. It's coming up because of the shot noise of the light inside the cavity. And here we're limited by thermal noise. So the scaling is completely different.
So in particular,
and the laser power only plays a role for scanning the frequency.
Do you think, so is the claim then that for a given laser power, you think that you could have a better scan average sensitivity than you would got from a broadband laser interferometer of the same power?
Well, we cannot build so resonance is actually very important in getting sensitivity in this detector. So if I took out the particle of this cavity from this cavity and just let it be a broadband Fabry-Perot cavity, there's no way I'd be able to see 10 to the minus 20 per root hertz strain. Because the gravitational wave applies a force on the particle, that resonantly gets converted into a very large displacement. That's a very crucial principle of working for this detector. So this detector can never be broadband, and a broadband detector could never have the sensitivity. A broadband Fabry-Perot or optical detector could never have the sensitivity.
Maybe we should leave this till later, but thanks.
Yeah. Okay. So So we looked at the noise of the photon recoil, and we have convinced ourselves by this time that disks and stacked disks should lower the noise. So what I'll show you next is the feasibility of whether it is even possible to trap disks or stacked disks in this kind of a setup. So for that, we mostly have to answer 4 questions. What is the transmission through the stack? What is the field inside the stack? What is the trapping frequency or the stiffness of the trap? And finally, can these things be fabricated in the lab? And when I talk about stack, what we'll usually talk about is something that is shown over here on the right, where you have some alternating layers of different refractive index material. So think of like a Bragg reflector, but optimized to, in fact, have a perfect transmission, whereas a Bragg reflector has been optimized to have 0 transmission or full reflection. So here what I did was studied what kind of thicknesses we could get, or we should use to actually get a full transmission. So one of the crucial lessons from this type of study was to say that if you have a symmetric stack, let's, for example, say a 3-layer symmetric stack. So you have some front cap, some end cap, and some center layer. And if you have whole number of quarter wavelengths in the end caps, and if you have even number of quarter wavelengths in the center layer, then the stack will be completely transmissive. It should have a transmission of 1. And of course, wavelength, by wavelength, I mean a modified wavelength, taking into account the refractive index of that respective material. So that's good. So if we build something symmetric, we should have a full transmission. That's first thing. Second thing we can ask ourselves is, okay, but like, what if in fabrication, I get certain errors in the thicknesses and I'm not able to hit the thickness exactly correctly? Then how much do I take a hit on transmission, or how critical is it to get the thickness correct? So that is shown over here on the right. Here on the x-axis, I'm showing the error in the thickness of the end caps, and on the y-axis, I'm showing the error in the thickness of the center layer. And this contour, 0.1 contour, is basically you'd want to stay within this 0.1 contour if you wanted to hit a 90% transmission. And if you wanted to hit a 99% transmission, you'd have to stay within this 0.01 contour region. So basically, we can use simulations like this to tell us how much error we can tolerate in transmission. And just to summarize that, essentially, if we wanted to hit a 99% transmission, we can tolerate a 1.5 nanometer precision in the fabrication. Or we could actually, if we fabricated 2.5 nanometer precision, we would hit the transmission of 99.9%. And from a fabrication perspective, this should be pretty doable. Okay, so the next question about the feasibility was, what does the field look like inside these stacks? So here I've done some simulations of how the stack modifies the field if it's put in a standing wave. So the standing wave here has an amplitude of 2 inside vacuum. And then you put a stack inside it. And you see that, first of all, you see that the stack has actually increased the amplitude of the standing wave. These different colors are just the snapshot of the standing wave at different times, so different values of omega t, if you say so. And then you see here that depending on the refractive index and thickness of the stack, you can get some amplification inside the stack itself of the standing wave, and that's mostly coming from this echelon effect from these end caps. And then we can look at all the other intermediate time snapshots besides just these 3 time snapshots, and those sample all the other amplitudes between the purple and the green curve. So we know what the field now looks like inside these stacks. And then we can ask the next question, what happens if I move the stack slightly? Does the field change, and how does it change? So I won't show you that here because it's a very complicated plot, but like essentially I have done those calculations, and those informed, once you know how the field changes when the particle moves, then you can compute the new potential energy as a function of the position of the particle. And then that can tell you what the trapping frequency you could get for a given amount of laser power. So I've done those calculations, and I've shown that in fact it is possible to trap these things with normal nominal amounts of laser power, what we would be using otherwise, because as you see that they don't really change the field very much. And the last question on the feasibility was, can we fabricate these things? I can't fabricate them, but thankfully we have other people in the lab who can fabricate them, and they have fabricated these discs. So over here on the right, you're seeing a SEM image of one of the discs close up. And over here on the left is optical images, where each of these orange circles is one disc. This is something people in our lab have fabricated recently. And so we hope to be able to use them soon. So I told you that the noise should be lower if we move from spheres to disks. And if we move from disks to stacks, the noise should be even lower. I showed you that these things are in fact trappable, and it is feasible to make an experiment with this, or at least all the things that we could think of. We have checked those. So now what is the sensitivity that we can expect from these disks and stacks? So here in the top dotted line, you're seeing the sensitivity from a 1 meter instrument with just a single disk. And then in the dashed curve, you see the improvement that you get by using a stacked disk. And then if you keep increasing the length, you get another factor of L improvement from the length. And then here in the 100-meter one, we've also made the instrument cryogenic. So over generations, we can think we will hit about 10 to the minus 22 strain sensitivity, depending on the frequency.
So just to ask,
so this was sort of,
is this again the locus
Yeah.
of the on-resonance sensitivities?
Yeah, absolutely. Okay. Yeah, this is the locus of the on-resonance sensitivity. Yeah.
Why?
So this is, yeah.
In your earlier, in one of your earlier slides, you had an equation for the sensitivity that went as 1 over L squared. Why is this not improving as 1 over L squared?
So that was in PSD, and this is in ASD.
Oh, this is the,
so that was,
I see. I understand.
Yeah.
Thank you.
Okay, so this is what we expect. So we wrote up this paper, and in parallel, we have actually started building some capacity in the lab to. So we haven't started building the Michelson. We're still waiting for parts like tubes and chambers to arrive for the main Michelson thing. But in parallel, we have started building another trapping experiments to trap these disks. So that's what you're seeing over here on the left is the optical table inside the vacuum chamber. And this is a top view of the same thing. And then over here, you're on the right, you're seeing this cavity and this slide, which holds all the small nanoparticles. And then you shake the slide with a very high acceleration and drop the particle in the laser beam and hope that it gets trapped. So we're starting to build this capacity in the lab to start trapping, and then eventually we'll get the tubes, the beam tubes and the chambers, and build the full Michelson. Okay, so how does the sensitivity compare with the sources in this band? So one of the most important sources at these frequencies happens to be the black hole superradiance, where you assume that you have some spinning black holes, say about 10 kiloparsecs away from us, and it forms an axion cloud around it from the spin, and these axions annihilate and create gravitational waves. So what kind of strains can we expect from that? And May and Masha improved previous calculations, they improved those and calculated it more precisely. And this is what they have shown, that the strain should be, if the thing was a 10 kiloparsec, we should be able to put some limits on this thing with the 100-meter instrument. Another way to look at this source is to ask what is the reach for that source. So here, let's just fix ourselves to this 100-meter sensitivity. And if you assume the 100-meter sensitivity, then Masha and May calculated the reach for the superradiance. How far will we be able to look for the superradiance signal? And so for a given black hole mass, for a given axion mass, you could look at about 50 kiloparsecs, which is the brightest regions. And the 3 different colors are different levels of superradiance from which the signal could be coming. The other important source in this frequency band is mergers of primordial black holes. And I say primordial because this frequency is high enough that everything above, or all astrophysical black holes, would have already merged at frequencies lower than 10 kilohertz. So if you do see a black hole signal above 10 kilohertz, it has to be less than 0.1 solar masses, which means it has to be a primordial black hole. So we sort of compared all of that.
So just to ask on, sorry, can I just ask on the primordial black holes, do you expect that to be a stochastic signal or a sort of distinguished signal?
Well, we could expect both depending on which models of primordial black hole formations you assume. So you could assume like a primordial black hole distribution of a singular mass, and depending on the density or the number of black holes within the Milky Way, a number of the binaries, a number of merging binaries in the reach of this detector. So these are, I would say, this is ongoing work right now. But to answer that question,
for the signal that you drew, is that a signal to is that sensitivity to a stochastic signal or sensitivity to a particular merger?
Yeah, let me show that on this
Okay.
plot, in fact. So on this plot here, just to put it in perspective of the previous plot, the dashed pink line is the solid layer line, which is the 100-meter sensitivity. And the dashed cyan line is the 1-meter disk sensitivity, so the best and the worst sensitivity that we can assume. And all of these solid lines, so for example, let's look at this green solid line, which corresponds to the strain from the inspiral of a 0.01 solar mass primordial black hole. So what you saw in that pink region in the previous plot was basically an envelope of all of these different mass. So this is sort of the possible signal space, so as to say, because any black hole, for example, the 0.01 solar mass black hole would merge somewhere between 100 to 200 kilohertz. So you wouldn't expect anything above that frequency for that black hole. So this is just sort of an envelope of all of the possible signals that could exist, assuming single end spirals.
Okay, thanks. So
yeah.
just one more question about things. What's the quality? What quality factor should we be thinking of for the like sensitivity loci? Should we be thinking of like 1,000 or 100 or something else?
So for in terms of fixing the bandwidth, we should be thinking of about 10 to 100. Is because the lower that you get the quality factor, we want to keep it low so that we can measure as many frequencies as possible. And the lowest we think we can get is about 10.
Okay, thanks.
And 100 should be very easy to achieve, yeah. Okay, so assuming that previous plot of how the strain of primordial black holes compares with the sensitivity of the detector, what I've calculated here is, let's say the detector runs for 1 year and we scan the frequency within 1 year. Let's say we sit at each frequency for 10 days. Then if we did that, what kind of statements would we be able to make about merger rates for primordial black holes if we didn't see anything during the entire year? So here, this would be the upper limit on the merger rate from the design sensitivity. And this would be the upper limit on the merger rate from the initial sensitivity from the 1-meter disk thing. And again, this is assuming the previous slide where you have single end spirals. And then you can use this upper limit on the rate to ask, okay, now let's assume certain models of primordial binary, PBH binary formations and how fast they merge and whether they merge in the Hubble time or not. And so again, there's a lot of theoretical different types of models that prescribe how often are these binaries should be merging. So they create rates given the mass function, given the abundance of PBHs in dark matter. So you could take any particular model and you can invert that form of the rate of the merger rate, and given the mass, extract out the abundance, the FPBH, which is how much abundance should primordial black holes be making off of dark matter. So here, what I've added onto this plot is the dotted curves, which correspond to the right axis, which is the abundance, which is the upper limit that this detector, if it ran for 1 year, could place on FPBH. And if you squint your eye, you could see that this upper limit is 10 to the 6, which is inconsequential because FPBH has to be less than 1. So the punchline is that even if we ran this detector for 1 year with scanning and 10 days at each frequency, assuming the current formation models, and if we assume that those theoretical models are correct, this detector will not be able to put any limits on the abundance of dark matter. It will still be able to put limits on merger rates because those don't have to assume any models. We can ask, or I asked, well, so this is the story in the band, in the high frequency band, but these same black holes also have a history where they were also spiraling in the LIGO band. So could we maybe place limits from them in the LIGO band? And this is what I have calculated, that if in LIGO we went in and analyzed data, so this is mass on the x-axis. So currently LIGO analyzes data only above 1 solar mass for binary mergers. If LIGO if at LIGO we did analyze data and looked for binary black holes below a solar mass, this is the kind of limits that we could put on FPBH, assuming the same model that I assumed in the last slide. And this is the dotted line over here. So we could start putting meaningful constraints in this mass range from LIGO, but it involves a lot of complicated data analysis for these lower mass binary black holes, because the match filtering gets computationally very expensive, which is why we haven't done it yet. One parameter space where you can actually use LIGO to put constraints on light primordial black holes happens to be if you go even lighter, in fact. So if you go to the left of this axis. So this is a project that I'm currently working on, where we are using now, instead of the binary match filtering pipeline, we can use the continuous wave pipeline of LIGO. So LIGO can put limits on continuous wave strain at each frequency. And that's just saying, so if we have very light black holes, their in-spiral is slow enough that those should just, within the observing time of LIGO, that should just look like a continuous wave of a fixed frequency. Because the black hole is so light and the in-spiral, you don't really see the in-spiral, you just see like a ringing. And so using that, we can actually start to put limits on rate at much lighter black holes. I mean, these limits are kind of, again, much higher than what the theoretical predicted rates are. So maybe not so physically interesting, but nonetheless, we can put limits using and this is using real data. All of these solid lines that I showed in the previous two slides are just what we could do if we did analyze. We have done the analysis, and this should be the upper limit. And this is something that we will publish soon. Okay, and with that, I will show what we could do with this, given that we couldn't put any limits on, for example, a primordial black hole fraction using a single detector. If we scanned, we asked ourselves, well, could we do something if we made a xylophone out of this? So for example, if we put multiple particles in the same cavity, such that the in-spiral went through the band and sort of rang each one of these traps one by one. So here the orange, for example, is like we put multiple beads or multiple disks and have them have a different trapping frequency in the same detector. The same detector could see multiple phases of the same in-spiral. If we did that, what kind of statements would we be able to make on the merger rate? So here I'm showing the limits that we could place on merger rates using the xylophone. So we do a little bit better, of course, now, because of course we're not scanning anymore. We just put all of them at the same time running for the entire year, which is much more powerful than scanning. And then on the right axis over here is the limits that you could place. Again, same model, assuming that same model on FPBH. So again, it's still higher than 1, even if you use the xylophone. So then I was, okay, let's go even more crazy. What if I increase the number of traps in the xylophone? Would I get any better limit? Or you could ask the opposite question. What if I reduce the number of traps in the xylophone? How much worse does the limit become? So that's answered over here, where I have now varied the number of traps. So the green line here, the 10 traps, is the work from previous slide. That's the limit that you would be able to place on the merger rates. And if you kept increasing the traps, you would sort of start to converge at some limit at around 30 traps. So if you put 30 traps equally spaced, you would basically span out the entire locus. So it would eventually just look like a broadband detector in that entire band if you put 30 particles inside that thing. So we can dream. And that merger rate, again, you can convert that and ask, how does that look in terms of FPBH? So we have now gone from 10 to the 5 to 10 to the 4, or a bit below 10 to the 4, but it still stays above 1. So still within, assuming these models, still not physically interesting. So then you can ask, okay, what next? So if we put more of these particles, even then we can't start to put limits on dark matter, abundance of dark matter. Well, one more knob that we have got is we could try to put even more mass in the stack. So here, what I've done is I've asked, can we put even more mass? Because that would increase the sensitivity. So to answer that question,
Can I
I
ask
just
one?
vary. Yeah.
Can I ask one quick question?
Yeah.
That I think you said this and I just missed it. When you want to put a bunch of the different particles in the trap and have each one have a separate frequency, what is the best way to tune the frequencies for the different guy? Because what I would have said is adjust the mass, but that's not what you're doing because you're about to adjust the mass here.
Well,
you just
you
use
can.
slightly different refractive indices or something, or
Yeah, you could use different refractive indices. You could use different masses. You could put them in different positions from the Gaussian profile in the cavity. You have different positions inside the cavity, and each particle will see a slightly different intensity. So from that, you could get a modulation of the power seen by the particle. So that you have all of these knobs, and I will show very quickly that the mass, in fact, you can still tune the mass to achieve the xylophone.
okay, thank you.
Yeah. So first of all, if we weren't doing the xylophone, if we just wanted to have a single detector and add more mass to it, what I try to answer, or what I try to ask is, will that still be trappable? Because presumably, if you infinitely keep adding mass, then you sort of lose, because frequencies go as 1 over square root of mass. So what I asked is, what happens to trapping frequencies if I put a lot of mass? So here I vary the thickness of each of the layers. So I1 and I2 are the integers that represent the thickness of these layers, which is a proxy for the mass. So what I found in this simulation is, okay, here I1 is the x-axis, I2 is the y-axis, and the color is the frequency, and the frequency of normalized with this omega naught, which carries all these other parameters like the laser power, the beam radius, the wavelength, and the density. And so what I find is that even if you increase the thicknesses 20-fold, you would in fact not take a hit on the trapping frequency. Like the most variation in the trapping frequency is only a factor of 2. So that's okay. If you kept increasing the mass of the particle, you will not lose on the trapping frequency. So basically,
just to ask, do you have any idea?
To really start to probe the parameter space of primordial black holes in terms of FPBH.
Sorry, I was just going to ask, do you know when this will break down?
Okay, this is the final thought. Let me
oh, sure, okay.
This is the last slide, yeah.
That's fine, carry on.
Yeah, so if we did a xylophone and with a lot of mass, again, in dream territory here, then we could probably start putting limits on primordial black holes. Okay, so I will summarize now. Say that I told you about a new initiative for high frequency gravitational wave detectors. It's a reminder to fill out the Google form if you're interested in that physics. Told you about a miniature gravitational wave detector that's based on levitated nanoparticles, which will work in the 10 kilohertz to 300 kilohertz band. The main limitation of this detector comes from gas damping and photon recoil. And based on that limitation, we have now proposed a new design which offers a 20 times improved sensitivity. And in that paper, we've also verified the feasibility of this design. I showed you what kind of limits we could set on primordial black holes. And also this, because it's a completely new frequency regime, it will set independent limits on superradiance as well. And finally, we could perhaps imagine or dream of putting a xylophone or heavier particles to improve the sensitivity even further. Yeah, thanks. So I'll take questions now.
Okay, thank you very much.
Sorry, that went very long.
No, that's fine. No, not a problem at all. So yeah, does anybody have other questions?
Can I ask one question?
Go for it.
You presented this superradiance bounds and superradiance calculations in one plot. Do you know if you took into account these axion self-interactions, which some people here worked on and just published recently? And does this change the story?
I do not know the answer to that.
I can...
The answer is no.
Oh yeah, you're amazing. There you go.
Zero self interactions.
Okay.
Yeah. It's I mean, I think when this thing was out, then we did not even know what would happen, right? And I know there's a recent paper, but yeah, it's no interactions.
And do you have an intuition if something could change if you take interactions into account?
I think the best people that will answer this are other people in the audience.
Yeah.
Yeah. So what will happen is that if you increase the self-interactions too much, you'll decrease the size of the cloud, and that will reduce the gravitational wave signal. So yes, past a certain point it will, but for particles such as a QCD axion, for things where the coupling is small enough, you can verify that this isn't an issue. So we can direct you to our paper, which does have these plots, but yes, for small enough couplings, not an issue. Increase it large enough, you will suppress. Yeah, any other questions? Actually, sorry, I just had...
Can I ask a question?
Yes, go for it.
So is it possible to levitate in this way spin polarized materials? So imagine I want to do something like diamond with many nitrogen vacancy centers.
Yeah, and I think people are starting to think about that. I wouldn't see why not. It would be a very complicated system because your trapping beam is also going to interact with the NV center.
Yes, exactly. But that's why my intuition for how the electromagnetism of that works out.
Yeah. So you would have like a double optomechanical system. I mean, and you'd have to do the calculations of what that interaction with the NV center, like somehow if that starts to contribute towards anti-trapping, I don't know.
I mean, depends on the polarization direction, right? I mean, yeah, which one do you want?
Yeah, or if you have like completely different colors, so one color does the trapping and doesn't talk to the NV center, and the other color talks to the NV center.
Yes, because after all, this high frequency range, basically you have an exquisitely sensitive force sensor you're building in the frequency range. So the question is, well, are there other things we should be looking for other than just gravitational waves? Yes, of course. Maybe the sensitivity in your initial designs is not good enough for the gravitational waves you want to do, but maybe a slight variation is good enough for something else.
Yeah, and like it's still worth building. Again, these source calculations is just what human brains can imagine given our prior knowledge, right? So it's still worth building it because we don't really, we've never looked at these frequencies, so we don't really know what we'll find.
Absolutely. A very nice talk. Thank you.
Oh, thank you.
So yeah, I had a brief question about the mass thing you were talking about. So you're saying that increasing the mass by some factor of, I can't remember, so of order 20 or so didn't affect it very much. Do you have an idea of, so in the limit, it has to affect it. I mean, we make the thing a gram or something, it's not going to be trapped. Do you have an idea of where that limit should come in?
It's going to start to come in from non-fundamental effects, right? Like, for example, it will come in from like drooping from gravity, like you're not because from just gravity, you're going to droop within the laser waves. So how big is the droop, right? Okay. Or it's just like not a tenable system anymore. But from just the pure, and if I make it too large, right? If I make it too long, right now it's still like only 20 lambdas, no, 20 by 2 lambdas, right? So still the number of cycles inside the stack is still coherent. So after you make, like if you make a 1-inch glass slab, right? Is the laser beam inside that glass slab still actually maintaining its phase, or does it lose phase from the molecules of the glass slab, right? So after a point, you're going to start to see other decoherence effects that you don't see if you make the crystal, if you keep it all just crystal in just a small number of wavelengths.
Yeah, no, I certainly agree those will come in. But even just, let's suppose that we had a magical knob where we could just turn up the density of our thing. At some point, like the laser power is going to not be enough to keep it in place. What sort of point is that?
Yeah, so let's see the density. So yes, when I talked about increasing mass, I talked about making the thickness larger. Yeah. The density is over here in the denominator, right? So if you increase the density, then you would need to increase the laser power correspondingly.
Okay, so the point is the thing is getting bigger, so it's interacting with more of the beam at the same time as it's getting more massive. That's sort of why it's presumably not
exactly.
scaling
and
up.
So the potential energy
Right.
Yeah, the K and the M sort of increase
They
together.
they cancel out in that sort of
is
sense.
the conclusion. Yeah.
Right. Okay.
Yeah. In this limit. Yeah. Yeah.
No, that makes sense. Thanks.
Nancy, can I ask another question? Is this configuration, so this particular cylinder configuration, oriented along laser beam? I mean, after all, I've got to actually load the trap in some way. Is this the orientationally preferred direction? It seems very non-trivial. Maybe it is. Maybe this is a big basin of attraction. Is that the case and it's known?
It is the preferred direction in that, like from a fundamental point of view, this is going to be the minimum energy configuration. But also you would want to load it such that you would want to design something such that the minimum energy configuration also corresponds with the minimum scattering configuration. So this is the configuration in which you would have minimum scattering loss. And it is also the configuration, like the cylinder would like to align itself with the beam. Yeah.
And how do we call, if we load it by dropping it? You said you were dropping it off the slide and into the things. So how
I
do
wasn't,
we?
but like, yeah, other people who are in the
Yes.
lab.
Yeah, but practical questions. Maybe it's not, but how do you stop that after it's going to oscillate around for a very long time? How do you damp that motion or call that motion, or is that trivial?
Yeah, it's not trivial, in fact. So this has been like quite a bane of existence for the optical trapping community. Some people use this is called loading the trap. Some people would load their traps at higher pressure in their chamber, and then they start lowering the vacuum, then they start like pumping the gas out. So again, you use the gas damping to stop the particle, or capture it. Yeah, so there's a lot of different techniques. In this group, we know that, so there's 3 different experiments, trapping experiments in Andy's group. One experiment has been able to catch the particles in vacuum. The other one is still trying, and we think it should work, but like, yeah.
Okay.
Real life is hard.
This is why I'm not an experimentalist.
Yeah.
One of many reasons. But anyway, thank you.
Okay. Yeah. Any other questions? I mean, just to return very briefly to the thing I was asking about at first, I think it would be interesting to, I mean, so for the real experiment, of course, it's very important to include all of the noise sources and all that. But from a sort of more fundamental quantum measurement perspective, it'd be very interesting to look into, if you just have the fundamental things, if you just have the shot noise and the radiation pressure noise and et cetera, what the frequency average sensitivity looks like in that case. That would be an interesting quantity.
Yeah. Yeah, I mean, I would say thermal noise is also fundamental, but yeah, like given that it is limited, so the shot noise, I should say the shot noise is from the detection beam, right?
Yeah,
not from the cavity beam. So you would, yeah. So we would have to vary the power of the shot noise and then answer your question. Yeah. So the detection beam. Yeah.
Okay. All right. Well, if there are no other questions, then let's thank Nancy again. Thank you very, very much for a nice talk.
Yeah,
and,
thank you.
Have a good weekend, everybody.
Yeah, bye.
Thank you very much.
Okay, bye. Okay.